Can you catch this? Or match this? Check this direct to your spinal axis.
Welcome to Catch This, the Military Medicine Podcast. In today's episode 1, we're going to deal with a topic that is very important to the operational physician. Many of you may get the opportunity to serve as flight surgeons and as diving medical officers, and for you this will become a problem that you deal with on a daily basis. But all of us in military medicine need to have a thorough, or at least a working knowledge of dealing with problems that develop in dynamic pressure environments. Now this is a very large topic, so we've broken it into 4 episodes. Today we'll be dealing with part 1, which will focus on the characteristics of the atmosphere and Dalton's law primarily. And as we move into episode 2, we'll move on to Henry's law and later the treatment of decompression sickness. The first question that comes to bear is that of course, why is this important at all? Well, when you look around you at the operations that you support, what you see is people doing stuff in unusual environments. And these unusual environments come with a number of challenges, and that's what we're really here to talk about today. So let's start there. Starting with the surface of the Earth, we move out into space, beginning with the troposphere first, followed by the stratosphere, mesosphere, thermosphere, and then the exosphere. Now, the easy way to remember this is in the mnemonic, the strong man's triceps explode. Now, what we're really focused on today is going to be dealing with the troposphere. And as you move in beyond that into the stratosphere, we're beginning to deal with space physiology, which really won't be relevant for most of us. So we'll focus our efforts down here on the troposphere. And one of the first things to note is that there is a relationship to the temperature and altitude. And as you move out into space, the altitude is going to decrease up to a point, and then it's going to begin to increase after that. But for our intents and purposes within the troposphere, we have a fairly steady decrease in temperature as we move on up. But more importantly to our physiology is looking at the composition of the atmospheric gases. Now, we do a little bit of rounding here, but for all intents and purposes, we'll be talking about the atmosphere being made up of nitrogen, 78%, and oxygen being 21%, with the remaining gases being about 1%. And again, a little bit of rounding there, and a lot of different gases mixed up in that 1%. But for the most part, 21% oxygen and 78% nitrogen will explain most of the physiology we're talking about. Now, the second thing to understand is that while the concentration of oxygen will stay the same throughout the atmosphere, it will always be 21%. But as our pressure decreases as we extend up into the atmosphere, the amount of oxygen available for physiological purposes decreases as you ascend in the atmosphere. Hopefully this is all review for you, but very important as we discuss these problems. A lot of what we'll be talking about in these episodes will be related back to the universal gas law. And you'll recall from your days in physics class back in college that the universal gas law is described as PV equals nRT. And it describes the relationship between pressure, volume, temperature, and the mass of the gas itself. Now let's start with the relationship between temperature and volume, and that would be described as Charles' law, which states that when pressure is constant, the volume of a gas is very nearly proportional to its absolute temperature, and we can see that in this slide. And if you look at the beaker on the right, as we increase the temperature, that energy causes those molecules to spread out further and increase the amount of space that those molecules occupy. So the volume becomes bigger. And as you decrease the temperature, as you see on the left, those molecules come closer together, decreasing the volume. And that can be related mathematically with the formula V1 over T1 equals V2 over T2. And while this isn't critically important to a lot of what we're going to talk about, it is part of the context of understanding the gas laws. But let's turn our focus to Dalton's law, which is much more important for today's discussion. And what Dalton's law states is that the total pressure exerted by a mixture of gases is equal to the sum of the pressures of each individual gas. Now, if you look at the beaker on the left, what you see is one gas. We have several molecules of hydrogen gas here. If you look at the one in the middle, we're dealing with the second gas, which is helium. Now, those two gases have their own pressure and exert a certain amount of pressure against the lid, and that's depicted by the number of weights requiring to hold those volumes equal. But when we combine the same gases in those two beakers into the third beaker, we have an increased amount of pressure. And so what we measure as our total pressure is then equal to the sum of the pressures of those individual gases. So where hydrogen was exerting 2.9 atmospheres of pressure and the helium was exerting 7.2 atmospheres of pressure, we combine them and they add summatively to create a total pressure of 10.1 atmospheres. Now what we'll talk about frequently is the partial pressure of these gases, and when we say partial pressure, we're dealing with the individual pressure, or the individual component of pressure that is being exerted by the individual gas. Now if we turn our attention to our physiologically active gases, we can calculate what the pressures in the atmosphere are going to be. So for oxygen, if you think that the total pressure in the atmosphere is 760 millimeters of mercury, we can simply multiply that times the 21% or 0.21 that we know oxygen makes up in the atmosphere. That leaves us with a partial pressure of 159.6 millimeters of mercury for oxygen. Now don't worry about memorizing these numbers, of course. The important thing is to understand that the numbers can be calculated and they become relevant when we talk about the physiological behavior and at altitude or at depth. Nitrogen, similarly, 760 millimeters of mercury, we multiply that times the 78% that we know makes up the atmosphere, and we get a partial pressure of 592.8 millimeters of mercury in the atmosphere for nitrogen. And for carbon dioxide, 760 millimeters of mercury times 0.0003, very low percentage of carbon dioxide in the atmosphere, which leaves us with 0.2 millimeters of mercury in the normal environment. Now looking at that environment a little bit closer, there are a few benchmarks that are helpful to understand. Here in Bethesda, we're sitting at approximately sea level. Now if I look up at the sky, what I will see is a column of air reaching all the way into space. And that column of air contains a certain mass of gas, and that gas then pushes down on me with a certain pressure. And we describe that pressure in units called atmospheres. 1 atmosphere of pressure is what I would be experiencing in terms of ambient pressure here at sea level. Now as I move up into that column of gas, I'm going to have less of that gas pushing down on me. So I will be experiencing less pressure. Okay, and a particularly useful benchmark is that if we move up to approximately 18,000 feet, or what we would describe in aviation terms as flight level 180, that pressure will be exactly 1/2 of the atmospheric pressure I'm experiencing at sea level, or 1/2 atmospheres absolute. But as I move down in the gas column eventually and then cross over sea level and move into the undersea environment, what I will now have is that column of gas pushing down on me with the additional weight of a column of water that is also exerting pressure on me. Now water, of course, is a lot heavier than air, so we get the equivalent of an atmosphere of pressure much quicker. And in fact, every 33 feet of seawater, we experience an additional atmosphere's worth of pressure. So at 33 feet of seawater, it will be 2 atmospheres absolute, at 66, 3 atmospheres absolute, and at 99, 4 atmospheres absolute, and so forth. Now there are several units we use to describe pressure, and the 2 most important ones are the atmosphere absolute and the pounds per square inch absolute. An important conversion factor is that 1 atmosphere is worth 14.7 psi. So you'll see both of those units used interchangeably. Now let's turn our attention back to Dalton's law for just a minute. Now you'll recall that Dalton's law said that the total pressure of a gas mixture is equivalent to the sum of the partial pressures of each of the component gases in that mixture. Now one of the component gases in our atmosphere is oxygen. And as we've been discussing, the total pressure in the environment is going to decrease as we increase in altitude. So as we increase in altitude, that then from Dalton's law would infer that the partial pressure of oxygen is also going to decrease. Now hypoxia is stated as an oxygen deficiency in the blood cells and tissues is sufficient to cause impairment of function. And that's defined by the partial pressure of the oxygen in the environment. So once we get to a certain point in that atmosphere, we can no longer expect to have enough oxygen for those tissues to perform or to function properly. So we would then describe that hypoxia in several different capacities. There are 4 specific types of hypoxia that we talk about in operational medicine. And the first is hypoxic hypoxia. And that would be what we've been talking about, the decrease in the amount of oxygen available to the tissues as a result of changes in the altitude. This can also come from malfunctioning equipment or from poor oxygen discipline. In the operational arena, our aviators spend quite a bit of time learning how to operate that equipment in order to make sure that they're delivering the right amount of oxygen to their tissues. The next type of hypoxia is what we would call stagnant hypoxia. Well, we don't want to get into a lengthy discussion about G-forces. Suffice it to say that if we're in a maneuvering environment in aviation and we turn rapidly, we will then increase the amount of force that is being exerted on our body, and that's what we call a G-force or positive GZ. Now, as we undergo those maneuvers, what happens is that the blood in our body is then forced into our lower parts of our body or into our feet, and that creates a pooling situation where we're no longer able to get oxygen into all of our tissues. While there's plenty of oxygen in the blood, it's not being circulated appropriately. So that would be stagnant hypoxia. The third type of hypoxia is what we call histotoxic hypoxia, and this is a result essentially of poisoning. Substances such as alcohol, medication, or cyanide can interfere with the ability of the body to use oxygen at the cellular level. The final type of hypoxia is what we call hypemic hypoxia, which is referring to the inability of the blood to carry oxygen. This can result from any state that's going to decrease the amount of hemoglobin or the effectiveness of the hemoglobin in the blood to carry the oxygen molecule. Specifically, we talk about carbon monoxide poisoning, or hemorrhage or anemia, which will of course result in a decrease in the amount of hemoglobin in the blood, and finally sulfa drugs, which can also impact the ability. So in review, the four types of hypoxia that we talk about in the operational environment are hypoxic hypoxia, which results from changes in altitude, stagnant hypoxia, which results in pooling of the blood as a result of G forces, histotoxic hypoxia, which is the result of poisoning from alcohol or cyanide or other medication, and finally hypemic hypoxia, which is a result of decreased oxygen carrying capacity of the blood, like we see in carbon monoxide poisoning, anemia, or sulfa drugs. Now, the real problem with hypoxia operationally is that its onset is very insidious. It's important to understand that the person experiencing the hypoxia is the least likely person to be able to identify his problems. And because it is so difficult to identify, we spend a lot of time in training teaching aviators and aircrew members, as an example, how to recognize their symptoms of hypoxia. Now, the good news is that the individual signs and symptoms will be fairly consistent. While your symptoms and my symptoms may differ, what you experience each time will likely be the same. And those signs and symptoms are listed on the screen here. And identifying those during the altitude chamber training sequence is one of the primary focuses. Additionally, during that training, we also teach our aircrew members how to operate the oxygen equipment, and what you see here on the screen is the emergency procedures for correcting the oxygen once those symptoms are recognized in the altitude environment. Now, the last concept I want to mention to you today is what we call the time of useful consciousness. Now, this is described as the period of time from the loss of oxygen supply or exposure to the oxygen-poor environment to the time when deliberate function is lost. Now, this is very important operational, particularly in the aviation environment. Once the aviator has become hypoxic, he has a limited amount of time in order to react to that and correct his oxygen scenario using the emergency procedure described on the previous slide. Now, that time is defined as the time beyond which the aviator cannot correct his oxygen system. And as you see on the slide, at flight level 180 or 18,000 feet, that time is as long as 20 to 30 minutes. So as long as those symptoms are recognized, there's plenty of time to correct. But if we are flying at an altitude much higher, for example at flight level 350 or 35,000 feet, that time diminishes to only 30 to 60 seconds. That doesn't give you a whole lot of time to recognize your symptoms and still leave time left to correct your oxygen problem. So it is important that these symptoms are readily accessible in their own recollection of their understanding of hypoxia. That concludes our first episode of Catch This, where we focused on hypoxia that results from Dalton's law. Join us next time when we turn our attention to the problems that result from Henry's law.